Okay, in today's lecture, what I'd like to do is to move into chapter 22, which are the reactions of aldehydes and ketones. Now, before I do that, I always like to set up the context of the upcoming 2 or 3 chapters. And that is that now what we're ready to do is we're ready to look at the preparations and reactions of carbonyl compounds. Now, carbonyl compounds are basically broken up into 2 different classifications. The first we're going to look at aldehydes and ketones together. So the ketone is with 2 R groups attached to the carbonyl, and the aldehyde is with just 1 alkyl group and a hydrogen. And those are always grouped together, as well as then the second group is going to be a carboxylic acid and what are called the carboxylic acid derivatives. And the carboxylic acid derivatives all have groups attached to them, which I'm going to call Y group. So a carboxylic acid derivative would be something like a carboxylic acid chloride, and I'll write the names of these in a moment. So we have what's called a carboxylic acid chloride. We have a carboxylic acid anhydride. And that anhydride is what we used in step A of the benzocaine synthesis in lab. And then we also have esters, and we also have amides, where the nitrogen group is attached to the carbonyl. So all of these have these different groups attached to the carbonyl, and I will give you a brief idea of why these are all grouped together and why they're important. The final one doesn't fit that particular mold, and it is what is called a nitrile, where the C triple bond N is attached to an alkyl group. So all of these groups are called carboxylic acid derivatives. And they're all going to be treated in chapter 20, I believe, 4, because after chapter 22, we'll go into amines in 23. But we group aldehydes and ketones together, and we group carboxylic acid derivatives together because of the similarity in how they react. I'm going to talk about more of this in this particular lecture, but let's go back and talk about and remind ourselves of what happened when we reacted a Grignard with either an aldehyde or a ketone. What happened in that reaction was the R- came in and attacked the carbonyl, and the pair of electrons went up to the oxygen. So that what I did was I formed an O- species, and we'll call this R', and the R' formed the carbon-carbon bond. Now, what happened when we reacted that same Grignard with a carboxylic acid chloride? You may have to go back and take a look at your notes, but the same thing happened. The R- came in, attacked the carbonyl, and the pair of electrons went up on the oxygen. So we'll call that R' as well. Now, what's different about these 2 molecules? In the case of the aldehyde, we have an H group. In the case of any of the carboxylic acid derivatives, we have a group that is potentially a good leaving group, or at least a leaving group. So what happens? Well, in this case, whenever I form a CO bond like this pair of electrons tries to come back down and reform the carbonyl. In order to do that, something has to leave. Well, what groups never act as leaving groups? Carbons and hydrogens. So can this R group leave? No. Can this R group leave? No. Can this chloride leave? Sure, chlorine's a good leaving group. So what happened was I would end up forming the ketone as I lost my chloride. And if you remember about the acid-chloride reaction, we always had two equivalents of the Grignard because then a second equivalent of Grignard would come in and add to now the ketone, so that what we would end up doing is we would end up adding two of the same alkyl groups. Oh, let me get my primes right here. And so we would add a second equivalent of the alkyl group. Now this O- tries to bring the pair of electrons back down, and what happens? Nothing can leave. So it gets stuck there. What happened when this group originally was a carbon or a hydrogen group? The Grignard would come in, it would add to the carbonyl, it would form the carbon-carbon single bond. Can this pair of electrons in this oxygen, can that pair of electrons be brought down and kick something off? No, because you've got carbons and hydrogens, therefore that molecule is stuck as well. So what happened? It waited around to get protonated by the H plus H2O to make our final product, which was in this case a secondary alcohol. Same thing would happen down here. It would wait around and react with H plus H2O to form the tertiary alcohol. And remember, two equivalents of the Grignard added two equivalents of that alkyl group to the carbonyl. So the reason that we are going to classify aldehydes and ketones as one reaction and all of the carboxylic acid groups and acid derivative groups as a second classification is simply because carboxylic acid derivatives have this group that could leave. Some are better leaving groups than others. But up here, aldehydes and ketones have a group that basically cannot leave. Okay, so that sets up the context of the difference between Chapter 22, that we're going to do now, and Chapter 24, which we'll do once we're done with this chapter in amine chemistry. Okay. So let's talk a little bit more about carbonyls, and I'm trying to mimic in my lecture what the book does. So the first thing that the book introduces is the idea that a carbonyl group can have a resonance structure by taking this pair of electrons and giving it to the oxygen. That would give the oxygen a negative charge, and it would give the carbon a carbocation. Now, this is not a very stable resonance structure, but it still contributes so that basically the resonance hybrid would have a delta minus charge on the oxygen and a delta positive charge on the carbon. So that means that the oxygen can react with electrophiles like H+, and the carbon can react with nucleophiles either like our Grignards, but we'll also find out what happens when they react with neutral nucleophiles like water and alcohol. Okay, so the carbonyl group will be reacting with the nucleophiles, and the oxygen would be reacting with the electrophiles. Now, I'm going to kind of foreshadow something that we'll need to talk about, because water and alcohol don't react with a carbonyl group very well. So in other words, if I just took a normal run-of-the-mill aldehyde or ketone, and that's the way I'm going to represent these, and I tried to just react it with water, the chances are I'm going to get no reaction. And that's simply because the water is a weak nucleophile. So what I'd like to do is, if I want to add water to that carbonyl, what I'm going to need, or any of the weak nuclei, including nucleophiles, including alcohol, what I should do is make that carbon more electrophilic. How do I do that? I basically take and add a H+ to my carbonyl. Remember, up here, the H+ reacts with the oxygen. So I'm going to donate my pair of electrons from the oxygen, and I'm going to form this oxonium ion. That oxonium ion has a resonance structure where if I take this pair of electrons and move it to the oxygen, I can form the second resonance structure, which basically looks like a carbocation. But the critical part here is that the overall charge on both of these species, on both these resonance structure, is or are +1. That means that in terms of the resonance hybrid, we know that the oxygen's not really going to want to have much to do with a delta positive charge. So basically, by adding the H+ to the carbonyl, we make this carbon is more electrophilic because it has a greater delta positive charge. Because overall, the species, both those resonance structures are +1. Okay, so we'll come back to that later in this lecture or at the beginning of the next one. But the key thing is I can add weak nucleophiles to the carbonyl, but in order to add weak nucleophiles, I'm going to need to add H+ first. Okay. Okay, so now the way that all organic textbooks are set up is to basically start with some structural features of that functional group, and then how do we make that functional group? And we always start with what reagents do we already know that we can use with different reactions to make aldehydes and ketones. Okay, and so reaction number 1, we can take this alkene and we can convert it into a ketone and an aldehyde. So, you're not going to like me for this, but don't care at this point, because we have to know our reactions and we've got to do some review along the way here. This is question number 1 on the take-home or on the online quiz. Type in the reagents that you would use, and you don't have to worry about super or subscripts. Type in the reagents that you would use to accomplish this reaction. You may have to look at Top Hat, you may have to look at your notes, but what would we do? I will give you a hint. This reaction is called overall oxidative cleavage. And it may have been from last semester. Okay. Reaction number 2 that we already know from this semester, the very beginning of this semester. If I took a terminal alkyne, what reagent would I use to convert that terminal alkyne into an aldehyde? That's going to be provide that reagent in question 2. Reaction number 3 is if I take an internal alkyne, what reagent would I use to convert that internal alkyne into a mixture of ketones? So again, type out the reagents in the box that you would use to make the ketone. Previous reaction number 4. How do you add a carbonyl group to a benzene ring? What reagent would I use to accomplish that? And let me give you some hints on how you can use the name if you'd like, or if you're going to draw the structure, how do you handle carbonyls in typing out a structure? Well, let's say I had this carbonyl. Let's say I had this aldehyde. I could write this aldehyde out by writing R and then in parentheses C double bond O and then H. That would be a way to type out this structure. Or if you had a ketone like this, you could write this R C double bond O CH3. So this is how you could type out, that's how you could type out that group, because you may need to do that with this one. So again, give what reagent, and if there's another reagent that would go here, then you need to do that as well. Okay, so here's 4 reactions we know from before. You're going to type in the reagents in questions 1, 2, 3, and 4 in the online quiz for this lecture. Are we done? No, we're not. Reaction 5. Let's say that we had a secondary alcohol, and I wanted to, the critical phrase, oxidize that secondary alcohol to a ketone. What reagent would I use? So question 5 is going to be, what reagent would I use to accomplish that transformation? You just have to type in one. There may be more than one. Unfortunately, I'm going to have to check all these questions by hand, but That's okay. So if you get them wrong to begin with, don't freak out, because I have to go through and grade all of these by hand. Okay, so there's that one, and there's another way to oxidize. So this was a way to oxidize to form a ketone. What about reaction 6? If I took this primary alcohol, what reagent would I use to convert that to the aldehyde? And again, there's more than one of those. Either the reagent, in this case, you could use the name. Okay, so the idea is we're reviewing these different reactions. Okay, so those are the first 6 questions in the online quiz for this lecture. Okay, now the next couple reactions are going to be new reactions, and these are going to be basically ways to prepare ketones and aldehydes. Some of them we will talk about the mechanisms when we get into chapter 24. So I'm just going to provide the reagent and maybe a little bit of commentary on it. But for the most part, we're going to talk about those mechanisms because there's something we need to know in chapter 24 for each one of these. So the first thing is, if you have an ester, you can reduce that ester down to an aldehyde. Okay, and it's going to require a special set of reagents. But let me tell you what reagent it's not. Okay, so this is going to be basically a reduction reaction. Now, if you're thinking reduction, I remember what that is. That's using either lithium aluminum hydride or sodium borohydride. Yes, absolutely, it is a reduction. But if you go back and you look at your notes, back when we were talking about these two reagents and carbonyl compounds, this reaction actually would end up giving you two alcohols where the two parts of the molecule, the carbonyl part and the alcohol part, would actually be broken up into two different alcohols. So this molecule cleaves. So this isn't that type of a reduction. Lithium aluminum hydride and sodium borohydride will give you the two alcohols and will split the molecule up. It's a reduction, yes. So how do you convert an ester then to an aldehyde? Well, what we need to do is we need to use, these are very reactive. Those are reactive molecules with hydrogen. And remember that each one of these reagents can donate up to 4 H's. So I'm going to take the approach here and say, you know what? I just want to donate 1 H. So what we need to use is we need to use sort of a less reactive aluminum hydride. And the reagent that is usually used, the one that Top Hat uses, is what is called DIBALH, Dibal. Now, that the DIB stands for should be diisobutyl. So diisobutyl is this 1, 2, 3, 4 with an aluminum. And then on the other side is the other isobutyl. and then by replacing 2 of the 3 positions on the aluminum with alkyl groups, you now only have 1 hydrogen that can react. So if you want to reduce and replace basically an OR with an H, you're going to use dibol for this reaction. Okay, and that's a reagent you just have to remember, and we'll talk more about this mechanism in chapter 24. Right. So that's one way to make an aldehyde from an ester, is to use a less reactive aluminum hydride, which is going to be dibol. Okay. Another reaction that you can do to make, in this case, a ketone, is to take our nitrile that we just learned about as a carboxylic acid derivative molecule, and what we can do is we can add to that another R group in the form of a Grignard reagent. And we'll talk about the mechanism of this reaction in chapter 24, but I want to introduce it because Top Hat introduces it. So I'm going to react these 2 together, and in essence what I'm going to do is I'm going to make a ketone by adding that R minus group and replacing the nitrogen in the C triple bond N. So this is a method to prepare ketones, and as with all Grignard reactions, there needs to be a then H plus H2O step. Okay, so we'll talk more about the detailed mechanisms though, but you need to know those reactions in order to okay, so before we talk about new reactions of these aldehydes and ketones, we should probably talk about the one reaction that we already know. Well, one. We know multiple reactions here of these ketones and aldehydes from our previous reaction, or previous material. So, how about reaction number 7 is, how would you convert a ketone or an aldehyde to an alcohol? That's going to be a reduction. How would you, what reagent would you use? You have more than one. What reagent would I use to accomplish that transformation? Let's throw in a couple more. I'll make this one specific. What reagent would I use to convert that ketone to that tertiary alcohol? Okay. So this is going to be question 7, and this is going to be question 8. So those reactions of aldehydes and ketones we already know. All right, let's talk about a new reaction. New reactions of aldehydes and ketones. So what we want to do is, let's talk a little bit about reacting an aldehyde or a ketone let's start with the idea of question, what question are we at? We're at question 9. For question 9, on your on the pre-lecture quiz or the online quiz, which is more stable? Ketone or aldehyde? And there'll be a checkbox to check either one. Question 10. Give me a short answer why. Now, let's do a new reaction. Let's take the aldehyde or the ketone and let's react it with H2O. I have a problem. My problem is that a neutral nucleophile like this will not react with a ketone, so I'm going to need to add acid as my catalyst to make this reaction go. What's going to happen in this reaction? What's going to happen is the pair of electrons on the oxygen is going to be used to bond the H plus, and there are two resonance structures, as you saw earlier. There's two resonance structures for this plus positively charged species. I could move this pair of electrons to the oxygen, which would leave a full-blown positive charge on the carbon. And I'm using, and just so you know, I'm using this HR to indicate that this would be the same mechanism regardless of whether it was an aldehyde or a ketone. Okay, so when I have these two resonance structures, it doesn't matter which one I'm going to react. I'm going to react both of them just so you show what happens. So what happens is my neutral nucleophile, in this case my water, can come in and add to that carbon, and if it does that, then this pair of electrons has to go to the oxygen. So if the water adds to that resonance structure, I end up with an OH. With a water down here, the whole water adds, so I end up with a oxonium ion, and we'll take it from there in a minute. If you use the resonance structure with the C+, the H2O will come in and react like every other C+ it's reacted with. And I'm still going to form that same oxonium ion. So it doesn't matter which resonance structure you react with, you're going to get the same product either way. Okay. So then what's the final step in this mechanism? Lose the H+, that's why it's a catalyst. And we're going to have now two OHs attached to that carbon. Over here we're going to get the same thing. We're going to lose an H+. And we're going to end up with two OHs attached to that carbon. Okay, so again, it doesn't matter which carbon or which resonance structure you're reacting with, you're going to end up with this product. Now, this product is called a hydrate. That's its name. And the next few molecules we're going to be making all have these sort of generic names. So this is a hydrate. Okay. So this is the mechanism by which we would form a hydrate. I'm going to go to the next slide and I'm going to write the overall reaction, and then we need to talk a little bit about it. So let me go to the next slide and let me say, okay, let's take our aldehyde or our ketone. Let's react it with H2O with an H plus catalyst. The final product that I'm going to form is this hydrate. Now the reactions, this reaction is one of a couple more we're going to do. We're going to make what's called a hemiacetal or a hemiketal, and an acetal and a ketal. And at this point I want to talk a little bit about the equilibrium in this reaction. For the most part, the equilibrium in this reaction, the equilibrium lies to the reactants. In other words, you get very little product in these hydrate reactions. And that's just the nature of how they work. We'll see all the different issues with this in the future, but the equilibrium really lies towards the reactants. There are a couple of molecules, though, that do have significant, if not all, of their equilibrium lie towards the products. So the exceptions where the equilibrium lies towards the products is the following. If I have two H's attached to the carbon, this is formaldehyde. And formaldehyde is usually used to preserve dead things. If you react formaldehyde with water, you do not need any acid. The equilibrium will lie to the right, and you will make the hydrate, and that hydrate in water is actually what is called formalin. So if, for instance, you had biological samples and they're being preserved, they're usually in either methanol, which is what I believe all the biology samples are, but they also can be in what is called formalin. So formalin is just the formaldehyde as it reacts with the water to form the hydrate. Formaldehyde actually itself is a gas. So if you bubble the formaldehyde into water, you make formalin solution. And so that's one situation where the hydrate is actually fairly stable. The other way to make the hydrate is to take the carbon and attach the carbon that's next to the carbonyl group, and that is to attach electron withdrawing groups, namely halogens. And what happens is the halogens pull the carbon, or pull the electron density out of the carbon, making it delta positive. Now, this carbon attached to the carbonyl was already delta positive, we saw earlier. So what it does is it basically makes this molecule unstable. Now, I'll give you a hint about question number 10 on your online quiz. What would you do to stabilize the delta positive charge on the carbonyl group? I'll give you another hint. The carbon-oxygen double bond is very much like a carbon-carbon double bond. So how do you make a carbon-carbon double bond more stable? Okay. Well, we'll end it at that. Those are your two hints. So if you take this molecule, this is called chloral hydrate. If you react that with water, you basically will form Sorry, I got that wrong. This is called chloral, and this is called chloral hydrate. So that reaction will go 100% as well. So these are the only two examples where the equilibrium lies towards the product. Okay. So otherwise, with just run-of-the-mill aldehydes and ketones, forming the hydrate is going to be, you're going to get very little hydrate, if any. The equilibrium lies to the left. Okay. Now, we've always talked about, you've got H2O. What is its cousin? Alcohol. So whatever I can do with water, I can do with alcohol. So let's set up that reaction. So let's take my aldehyde ketone and let's react it with, let's just make it simple. Let's react it with methyl alcohol. Now the problem here is, this is again a weak nucleophile, so I'm going to need help. I'm going to need the acid catalyst. So the oxygen of the carbonyl is going to react with the H plus to form the oxonium ion. The methanol, like the water, is going to come in and add to that carbon. That pair of electrons goes up to the oxygen. Now, all these are going to be equilibrium steps. So I'm going to end up forming the OH and the whole methanol water molecule adds so that I get an oxonium ion. What's the next step? Lose H plus. And if you're having a sense of deja vu, basically we just did the hydrate mechanism with an alcohol instead of with water. Same steps. Okay. So this is actually, depending on whether the original molecule was an aldehyde or a ketone, this molecule is either called a hemiacetal if you have a hydrogen from the aldehyde, and it's called a hemiketal if you started with a ketone so that the R group, you have two R groups attached to the carbon. Okay, so you're saying, well, wait, I think hemi means half. So I just made a half of an acetal and half of a ketal. So, you know, my next question would be, so what's a full-blown acetal and what's a full-blown ketal? Well, that would be a good question. Typically, what you can do is you can either add one or two equivalents of alcohol. So if we started with two equivalents, what I would then do is, remember, I have an H plus. The H plus is from the final step. So what I can do is I can protonate one of these two oxygen species. I should have asked what's going to happen, and you would have said protonate the oxygen. Well, which one? Well, the thing is, if I protonate the methanol, I'm going backwards. So I'm not going to do that. Or if I did that, I would go backwards. I'm going to protonate the OH because that's going to take me forward. So now I just protonated my OH, and it becomes water. What happens next? You guessed it, you lose water. And we form that carbocation. My second equivalent now of methanol comes in and adds to that carbocation. So that I whole molecule adds, I have my oxonium ion, and now I'm going to lose H+. And I need to write that. I'm going to write that over here because I'm running out of space. And so what did I just make? I just made either the full-blown acetal or the full-blown ketal, depending upon, again, whether it started out as an aldehyde or whether it started out as a ketone. Okay, so this is the mechanism to form a hemiacetal or ketal, and also then to form the full-blown acetal or ketal. Let me just finish up because I've got 2 minutes left. I'll just make it a ketone, or make it an aldehyde to start with. So if we add 2 equivalents of methanol, let me write the overall reaction. I have my acid catalyst. I'm going to form my full-blown acetal. Well, we talked about with hydrates, where does the equilibrium lie? Does the equilibrium lie with the reactant or the product? And for acetals and ketals, the equilibrium still lies towards the reactant side. So basically you would have equilibrium arrows that look like that. You don't get much acetal formation normally, or ketal formation. What we'll start with next time is actually how you get how you push the equilibrium to the right, and that reaction also then allows us to do what's called protection and deprotection. So that's going to be the next lecture. So in terms of your online quiz, I'm going to post the online quiz. Will be available when this lecture video is available. Questions number 1 and 10 come from providing the reagents to this that's in this video, and then I may throw in a couple more questions, just kind of matching of the different reactions that we've done. Okay, so that's going to be the online quiz. It'll be available when this lecture video is there. So my time is up. If you have any questions, email Piazza bring them to the Zoom question meetings at 8 or 1 p.m. Goodbye.